All right. Hello, everyone. As we are getting back into things here and starting to kind of get back into the flow of class and picking up some new stuff, our next topic is going to be geospatial data analysis. And for this week, we will be focusing on a thing called vector data, and I will delve into that more in a moment. And the way that we're going to be sort of handling that with Python is through the package called geopandas. So first off, I wanted to get this video out last Friday, but unfortunately, I spent a lot of this weekend in the vet office. My cat got really sick, but she's doing good now. And so since she's the cause of the delay here, I figure I might as well show her off a little bit. So here she is lounging in the backyard under our bush here. So again, apologies. I wanted to get this out earlier, but here we go. We've got a little troublemaker. Anyway, so with that, we have in the past few weeks looked at some ways to handle sort of scientific data, mainly through the view of arrays and NumPy, and then also started to get familiar with data tables or data frames via pandas. And so these are sort of the two representations that we've seen. And so on the left here, we've got our arrays where we have, the examples of 1D, 2D, and 3D array. And of course, you can go up higher from there into more dimensions, but these are the ones that we can draw easily and kind of have a intuitive representation for those. And then similarly, the data frame has sort of, in this case, sort of a 2D array type arrangement of stuff, but it's got some nice things tacked on that are like better for humans to read and be able to understand. So things like column names and rows can be selected out, and then the data internal to that data frame can be manipulated via these aggregate functions, such as the grouping to get like things like the month of year and so forth that we've already seen. But map making and geospatial analysis is important, especially in earth and environmental sciences. So, you are probably very familiar with seeing data on maps. So on the left here is one that's sort of more suited to our field of study. This is from the drought monitor, but you can see that the data is definitely not in a single sort of array sort of format. There, it's irregular and it's got all of these boundaries, and we want to be able to plot it on a map with state outlines and things like that. And then on the right, as we saw during the pandemic, there's been tons of sort of data visualizations trying to explain the state of the world and sort of explain what we know about how COVID spread. So this is one from the New York Times where they have the COVID cases colored by country. And so these are both ways that you can represent data on maps in a geospatial sort of way. And this is not something that we've sort of seen yet as something that we can do. But we know that it's very important and makes explaining data much easier. So this is where we would like to get to, is to be able to make things like this. And to do so, we need to understand that there are kind of two different types of data associated with this sort of geospatial framework. So a lot of times what you'll hear is the phrase geographic information systems, or GIS. And this is sort of a broad field of study that has been looking at these types of data and ways to manipulate and analyze and all of this for a very long time. And throughout that time, there's been a coalescence around two main data representations. The one on the left here is a raster. And this is more or less an array-based type of approach And so, if you have an image that might be like satellite imagery, for instance, if you zoom in enough, there are pixels, and those pixels are actually like numeric representations. But there is a way to map between this numeric representation and where it is on the Earth, more or less. And so we're not going to be looking at raster data today, but we will in the near future. And you've already kind of seen a lot of ways that you can think about it via arrays. On the other hand, the second type is vector data. And so this is, instead of saying the data needs to be on a fixed grid or something like that, we're a little bit more flexible, and we're trying to describe more or less geometries. So the kind of hierarchy that you will often see is at its core, the simplest thing that vector data can be is a point or multiple points, and these are XY locations, for instance. Like things like where you would be collecting data, like where is your data collection happening? And there can be, these vary continuously rather than discretely. So there's not like a fixed jump between different locations like there is in an array. So these can be sort of unstructured. They can vary continuously. And then similarly, once you have points, you can sort of connect them together as lines, as you can see here in the second level. And then once you connect the lines, you might go ahead and sort of want to denote a space that is closed by multiple points that are connected by lines, and that would be a polygon. And there are actually like higher levels to all of these, so you can have like collections of points, collections of lines, or collections of polygons as well. But this is the idea behind vector data. It's saying you can let the locations of where your data exists, or the space that it defines, vary continuously and be a little bit more amorphous compared to raster data, which is very structured and falls on a grid. So like I said, today we're going to be looking at vector data, or not today, but in this lesson, we're going to be looking at vector data and all of the things that go along with that. And so I just want to give a little bit of background in thinking about why this type of data exists and some of the things you need to think about with it. The main thing is, in geospatial, Earth isn't flat. And so we've got our little Descartes here going, oh no, like, all of these things are represented by XY points. So, that's sort of like a Cartesian representation of this data that I'm claiming can lie on a globe. And so we have to think about this a little bit. And this is actually a very challenging thing. And I imagine that those of you who are familiar with this type of data have already kind of beat your head against the wall here. And so the main thing here is, the Earth isn't flat. I mean, or is it? But I mean, like, no, it's not. So anyways, aside, the reason that we have to contend with this fact is because it is mathematically impossible to map a sphere onto a plane with no distortion. And the way that this is usually sort of described, or the metaphor is trying to unfold an orange peel or something of that sort. And you can't do it without sort of cutting into it. And then even then, there are still these sort of areas where you can see that there's still curvature. So there's no way to do this mathematically with no distortion. So that means there needs to be choices that are made in how you actually take these XY points and put them on a 2D screen, for instance. And so to get around this, the idea is we can project the sphere onto a plane, and you can try to preserve certain properties. So here we have sort of like this very coarse latitude, longitude type grid, where we have some angles that are or point, and then you would map those into some 2D space, which are new X and Y values, which will go into our vector data. Now, there are different projections, and the way that they work is going to, as I said, preserve certain properties. So you might want to preserve angles, or you might want to preserve area, and so forth. And so this is really sort of an art more than a science. And there are many ways to do this. And of course, there's an XKCD for it. So I'm not going to, read through all of these, but here it's just sort of it's a humorous interpretation of, which map projection is your favorite and what it says about you. And there are many more map projections than just these, but these are some of the most popular, as well as the most obscure, for instance, the Waterman butterfly and the Dymexian. Being sort of obscure, but things like the Robinson, Mercator, and Gall-Peters being very popular versions. So what you choose to use as your plotting representation is entirely up to you, but know that there are many ways to do this. And so one other thing was I found this sort of gem, which was what happens if you use different projections. If you took this 2D weird picture of a guy's head, maybe cow, who knows, person's head, and then you get some fun ones. Like I think this was probably trying to sort of dunk on the Mercator projection, because this makes people look weird, but I can't find the original citation, so we'll have to live with what we got here. Anyways, so there's some things that you should be aware of. There's a really long history of the software for this type of stuff, and because this is actually sort of a hard problem, we still rely on some of the older things that are very well developed, even though they don't sort of have the modern feel to them. So the kind of base one of the base sort of packages for this is called GDAL and OGR. GDAL is for raster stuff and OGR is for vector stuff. And you can kind of look at this and you can even see that these logos look kind of old and meh. But there's tons of GDAL has so much functionality, so we don't want to throw that away. So a lot of stuff is built on top of that. And likewise, there's this thing called GEOS, which I actually didn't even know the acronym for until today, Geometry Engine Open Source. But this is another popular sort of, I guess I'm going to call it backend or under the hood software package that's used by a lot of stuff. So if you've ever heard of QGIS or GRASS or any of these other ones, but so this is really a sort of fundamental building block. And so eventually, if you are building a lot more in-depth geospatial stuff, you'll probably bump against GEOS, GDAL, or OGR. And not going to get into it today, but it's important to kind of understand that, because it is actually it's pretty thin to go from geopandas all the way down into these. So just a really broad overview of the geospatial landscape in Python. It's large and we're only covering a tiny bit. So I do want to just shout out all of these packages and kind of walk through these one by one. So there are kind of what I'm calling raw bindings for GDAL and OGR. And if you try to use them, what you'll find is they don't work like other Python packages. They kind of, in my opinion, suck to use. They're great in their capabilities, but not in their usability. And so people have built things on top of that for GDAL and OGR. There's Rasterio or Raster.io, depending on how you want to pronounce it, for GDAL type stuff. So that's raster data, as you can kind of glean from the name. And then there's Fiona for OGR. I'm not sure why it's called Fiona, to be honest. I haven't had to use it very much in my time. There is also Shapely for higher level support for vector and geometric analysis. I've used that mostly over Fiona, and that has been fairly easy to use and quite nice when you have to drop down that low. But the thing that we're gonna do today is or in this sort of set of lessons is look at geopandas, and it has really good support for merging data and geometries. So this is like basically saying I want to use vector data, but I want it to operate like pandas, hence geopandas. And then finally, I just want to throw this out there because this is what we're going to try to cover next week or maybe the following week, depending on how things are going. But the best way, and like this is, I'm going to say this like as an unopinionated thing, although people may disagree, but the best way to work with raster data and other forms of labeled and multi-dimensional arrays is X-array. And so we'll cover that in the future. So with that, we're gonna, in the next section of this, it's gonna be a separate video, but we're gonna jump to VS Code. We'll walk through the installing of GeoPandas, and then I will give you a very high level overview of things that you can do with it. All right, thanks for watching, and I'll see you in the next video or in class.